Hello, Royals. For lesson 4.8, you should probably, if at all possible, you should print out the file 4.8.0 handout and follow along as I go through this. You can read the printed lesson as well, but just to figure out the tool for figuring out how many solutions there are to a triangle, it's something you're going to want to watch. The first thing that we need to do is make sure we realize when we don't need any sort of fancier tool. So I want to walk through these examples with you and show you that we could waste a lot of time using sine laws and cosine laws here, but in a number of them they're not required. So the very first triangle, keep in mind these triangles are not drawn to scale. Why don't you grab a ruler and try to draw a triangle that has a side length of 2 units and then a side length of 3 units, and then the other side being 6 units long. Well, you're going to have a hard time doing that. This is a pretty important triangle inequality. I like to think of it as kind of like the shortcut definition, that in Euclidean geometry, that's a geometry where you imagine there is such a thing as a two-dimensional surface that doesn't loop around on itself, the shortest distance between 2 points is going to be the straight line. This triangle then represents someone taking a detour. That should take longer, but its distance is shorter. Now, if you didn't recognize this, the cosine law, which is which law you would be set up to try to use here, is just going to fail for you on every single one of these angles. But it's going to take a long time for you to do that. Would you then erase your work thinking you did something wrong? Are you going to try to solve all 3 angles? You should be able to spot right away that there is going to be no such triangle. There's no solution. The triangle inequality says that in any triangle, any side needs to be, I always get this wrong. Let's see, that it has to be less than or equal to greater than or equal to the sum of the other 2 sides. Nope, it is less than or equal to the sum of the other 2 sides. 2 plus 3 needs to be bigger than 6. Yeah, you can see how I feel about trying to memorize. The second situation, I don't think I need to jump in and use a tangent ratio or a sine ratio or a cosine ratio. It's going to fall apart. This is supposed to be the longest side. That's supposed to be the hypotenuse. There's no solution. Okay. In this triangle, it looks like you have more information than is required. Be careful. Sometimes having too much information is a bit of a hint that there's something wrong here. With angles of 60 degrees and 10 degrees, I suppose I could calculate this third angle right here, but I think I have enough information to write a conclusion. Notice that across from a smaller angle of 10 degrees, I have a larger side than 4 meters, and that just can't happen here. This would be 110 degrees, and that's not my concern that what should be an obtuse angle is drawn as an acute angle, because I'll keep in mind these triangles aren't drawn to scale. But across from the largest angle should be the largest side. This isn't, again, another rule that you need to memorize. Just draw yourself a triangle. Where's the largest side going to be? The largest side is going to be across from the largest angle. Where's the smallest side going to be? The smallest side is going to be across from the smallest angle. That's not the case here. So again, there's no solution. And I don't need a fancy tool or even a sine law or a cosine law to tell me that. I guess the opposite of having too much information is having not enough information. If I tell you there's an angle of 60 degrees and an opposite side of 5 meters, let me pretend this 5 meters is actually a little bit smaller. Well, maybe not. If I make that 5 meters, I think I should be able to draw 5 meters there, and I should be able to draw maybe 5 meters there, and I should be able to draw 5 meters there. There's not enough information, so there are an infinite number of possible triangles. Infinite number. Okay. There are some rules that we might need to memorize. Like if I take a look at this if I look at this 70 degree, 80 degree, 40 degree triangle, that is what? A sum of 190 degrees. There's no such triangle. There's no solution. The rule that is being broken here is the angle sum of the triangle theorem, that the sum of the interior angles has to be 180 degrees. So what if I have a triangle where the sum of the interior angles is 180 degrees? There's 50 degrees and 60 degrees and 70 degrees. That's 180 degrees. If I don't give you any side lengths, that's a bit of a hint that there's something else going on here. There are an infinite number of similar triangles. The reason why I can't solve for any side lengths is because there is no one side length. Infinite number of triangles. Okay. Keep your eyes open for those situations. The last four situations are situations where we are set up to use the sine law to solve for an angle. And that situation where you're using the sine law to solve for an angle is called the ambiguous case. Sometimes people say the ambiguous case is when you have two triangles, and that's not true. If it's ambiguous how many triangles there are, that means I don't know how many triangles there are. And I'm going to pretend I don't know how many triangles there are in each one of these. The diagram, it looks like there's one such triangle, but these diagrams are not drawn to scale. Okay. Let's just try each one of these out. In each one of these, let's say that we're set to solve for theta. And notice in this case, and I think this is the demonstration that I'm going to do on the back as well, I'm keeping the angle and the side next to the angle, that adjacent side, fixed. And I'm just changing this length. I'm starting it off small. I'm making it a little bit larger, and then a little bit larger as well. This should be a review of our homework then, showing us how by just trying to use the sine law, if there is one answer, the calculations will give us at least one answer. If there's no answer, the calculations will tell us that. And then if there is at least one answer, we just need to check for the possibility of a second answer. Let's try it out. So in this case right here, I would say that the sine of theta divided by 8 would equal the sine of 30 degrees divided by 3. Sine of 30 degrees is one of my favorite ratios to use because I know that the sine of 30 degrees is 1/2. That means when I multiply both sides by 8 here, I'll get 1/2 of 8, 4/3. Well, the sine of theta will never equal 4/3. The ratio of y to r cannot be greater than 1. Your calculator would tell you this. If you try to take the inverse sine of 4/3, it'll say error 2. There is no solution. And what we'll illustrate on the back here is that this side length 3, if you draw this to scale, that shortest distance right there is 4 meters. The 3 meters is actually not long enough to hit. If you paid attention to that number right there, then maybe you can tell me how many solutions there will be in this case. Let's see what the sine law does. Sine of theta divided by 8 would equal the sine of 30 degrees divided by 4. I multiply both sides by 8. The sine of 30 degrees is 1/2. 1/2 of 8 is 4. And now this is where SOHCAHTOA, another case where SOHCAHTOA kind of falls apart. A grade 10 student might say this is impossible. You can't have an opposite side equal to the hypotenuse. The hypotenuse needs to be the longest side. If we use an XYR definition, though, when would the y value and the r value have the same value at a rotation of 90 degrees? I don't need to consider a second solution because 90 degrees is neither in the first quadrant nor in the second quadrant. There is only one solution. Sometimes I say there's one right solution, meaning it's the right angle, but then students think that that means there's one correct solution. One solution, it is going to be a right triangle, a 90-degree triangle, if you like. Okay. The next case, same calculations. Sine of theta degrees, sine of theta divided by 8 is going to equal the sine of 30 degrees divided by 7. Then I'll get the sine of theta equals 8 times the sine of 30. In every single one of these cases, I don't know why I keep doing that calculation over and over again. It's going to be 4. Well, when is the sine of theta going to be 4/7? Let's use a sketch in standard position to see. Go ahead and imagine a circle of radius 7 and draw the line y equals 4, or go 4/7 of the way up your circle. And you'll see that there are two solutions to the equation, which means there's a possibility for two solutions here. So I'm going to say that I think that theta 1 is going to be the inverse sine of 4/7. If we're working without a calculator, I'm going to say theta 2, maybe question mark, wonder if there's enough space for it here, is going to be the supplement of that angle. This is how I've expected students to work without calculators in the past. You do not need a calculator to demonstrate an understanding of this fact. What I would feel more comfortable knowing here is if there actually is room for that second angle, though. So I'll use a calculator to figure out what the inverse sine of 4/7 is. Tells me that's about 35 degrees. Okay. Theta 2 possibility then, the supplement of 35 degrees is going to be 145 degrees. Now, there is enough room in this triangle to have 30 degrees and 35 degrees. That would leave me with 115 degrees up there. There is also enough room for 30 degrees and 145 degrees. Those are the two possible triangles. I don't know. It's ambiguous. It's unclear in what direction this arm is going. Do not assume that this angle is obtuse just because it looks like it's obtuse on the diagram. The diagrams are not drawn to scale. There are two solutions here. What can be difficult to tell apart are these two situations. That if I make this side length just a little bit longer, that there's not going to be room for that second angle. Let's see what it looks like from the sine law. Sine of theta divided by 8 would equal the sine of 30 degrees divided by 9. One last time, 8 times the sine of 30 degrees is going to be 4. I get 4/9. There is definitely one solution here. The inverse sine of 4/9 is going to be about, inverse sine of 4/9, I'm in degree mode, 26 degrees. Okay. Now, maybe I'm not entirely sure that there is or isn't a second solution, so I try calculating theta 2. Theta 2 would be 180 degrees minus 26 degrees. But notice that making this side longer makes this angle smaller, which is going to make its supplement larger. And I do not have room for an angle of 154 degrees and 30 degrees in a triangle. It breaks the angle sum of a triangle theorem that says the sum of the interior angles of a triangle has to be exactly 180 degrees. So I'll just lightly cross this out and say that that angle is too big. You want to show your work for your reader, just like in a quadratic. If you're answering a word problem where there is a second solution, but you want to dismiss it, show the solution, then dismiss it. There is only one solution here, one such triangle. So this is kind of where the similarities between triangles and quadratics end, because with quadratics, if we're talking about the number of x-intercepts that a quadratic has, it either had 0 or 1 or 2. We went from 0 to 1 to 2 if we just lower our optimal value, I suppose, assuming that the curve is opening up. But with triangles, with sine law, ambiguous case sine law triangles, we go from having no solution to one solution to two solutions to one solution. And that's what I'm going to try to illustrate on the backside. Okay? Make sure that you are using grade 11 trigonometry here. These look very much like grade 10 trig problems. Your grade 10 teacher should have just avoided this situation for you. I don't think there ever would have been a case on a test where you were given this situation and you just weren't told about the second solution. If you've taken physics already, your physics teacher might have told you to just stick to the cosine law because the sine law causes problems. We can't do that in this situation. Usually in a physics class, you would have more information that you could use. Okay, so let's develop a discriminating tool. What we're going to do is we are going to imagine a triangle ABC. Sorry, I'll get this straight for you. And we have two different cases we need to think about. We need to think about what if A is acute or A is obtuse. Let's start with A being acute. So go out ahead and draw a triangle in each one of these cases. I'll draw a generic triangle here though. Say here's the angle A, there's side length A, and let's call this side length right here B. Okay. So in every single one of these situations, we would want to take a look at this distance. This distance, the height, the perpendicular distance there is a very important distance because it is the shortest distance from the vertex C to side length C. And we're going to use that right away. You're going to see an expression show up that for there to be at least one solution, side length A needs to be longer than that. In this triangle, let's just use a little bit of right angled trig. I'll say that the sine of A is going to be the ratio of H to B. That's me just using either Y to R or opposite to hypotenuse. That means that my shortest possible distance is going to be B sine A. We sometimes refer to this tool instead of as the discriminant. We can consider it a B sine A approach if you like. So now in this specific case, let's illustrate what happens if your side length A, angle A is fixed, side length B is fixed. What if your side length A is shorter than the shortest possible distance? And say it out loud. This side length is shorter than the shortest possible distance. And this means that A is too short, or it's not long enough to touch side length C. And that means that there is no solution. We saw that happen in the example yesterday. Okay. What we're going to do now is just imagine that we keep all of the other quantities fixed, and we're going to make A a little bit longer, like we did in the last 4 examples. If you're having a hard time visualizing this, think of this as a fisher person who has a rod, and they need to keep that rod at a fixed angle, and here's the surface of the water. If they don't let out enough line, then their line won't touch the water. If they let out a little bit more line, if they let out just enough line, keep in mind we don't know the length of this side. That's also ambiguous. We know this distance, we know this angle, and we know we can calculate that shortest distance. If A is exactly the same as that shortest distance, then the fisher's line will be just long enough to touch once. A is just long enough. It is the shortest distance, which means that it'll intersect at a right angle, at an angle of 90 degrees. It is just long enough to touch once. Let's say at 90 degrees. So there is going to be one solution, and it will be specifically a rectangular triangle. I'll say right-angled triangle. Okay. There's A. Here's all the positions that A could be in, but none of those create triangles. This is the only one that will create a triangle. Okay, let's make A a little bit longer. Let's make A longer than the shortest possible distance, but keep it shorter than this side. Keep the length of your line, of your fishing line, shorter than your fishing rod. That would look a little something like this. There's B, there's A, fixed. There's your shortest possible distance. So you are longer than your shortest possible distance, but shorter than this distance. And then swing that line around to show all of the possible positions that it could reach. And you'll see that you'll have 2 possible positions. Here's the angle that our calculator will tell us, B1. Here is the angle that our sketch and standard position will tell us, B2. Okay. There is, the A values are actually the same, but they're kind of in different positions, A1, A2. And that means that there will be 2 different angles for angle C. C, I guess that would be C2, and that would be C1. So let's say in English, A is long enough to touch once. Oops, sorry, not French. Touch once, and short enough to touch twice. And that statement, short enough to touch twice, will make a little bit more sense after this last example. Last acute example, sorry. That means you will have two solutions. One an acute triangle, one an obtuse triangle. In the last case, we actually don't even care about the height. It's the one situation where we don't really care about the height. If you have a situation where your side length A opposite the known angle is greater than or equal to this distance right here, this will be a little bit different because I'm drawing out lots of different possible lengths. Then there is definitely going to be a triangle. There will be exactly one triangle. If you try rotating this line around here to touch for a second time, you won't be able to create a second triangle. Okay, it would just loop back on itself. You would have an angle going up there and then down there, and that's not a triangle. Sometimes students say, well, wait, what if it's long enough? Wouldn't it rotate back here and then you would have another triangle out to the left? But then that would make the angle A obtuse. And there shouldn't be any ambiguity about the size of one angle in your triangle. So you don't need to worry about that second solution. We'll deal with it in the second at the bottom of this page. If A is greater than or equal to B, just pay attention to the inclusive case. You don't need to memorize this. You can always see it in a construction. Draw it out yourself. You can say that A is long enough to touch once. But too long to touch twice. This is what it looks like in our sine law when we don't have room for that second angle, when we break the angle sum of a triangle theorem. Okay. The situations if A is an obtuse angle are quite a bit simpler. So go ahead. You need to imagine that this is maybe like a fly fisher, or I'm not sure how else or when else you would hold a rod up like this. So the angle A is obtuse. Here's side length B, which is fixed. Notice if A, for A to be able to touch the water over here, not the ground behind the fisher person, A is going to need to be longer than B. If A is less than or equal to B, you will not have any triangles. A is too short. There's no triangle. And this is another situation where drawing a sketch is going to be way easier than trying to memorize this, because look at these two statements. These two statements are very, very close to each other. The inequality is just pointing in the other direction. Here's an inclusive case where you will have a solution. Here's an inclusive case where you won't have a solution. It is not a good idea to try to memorize that statement. Draw it out. What happens if you have an obtuse angle and the side opposite the given angle is longer than the side adjacent the given angle? Well, then you're going to be long enough to touch once. There is no second solution here. You already have one obtuse angle. There's no room for a second. There's no room for a second obtuse angle. A is long enough. There's one triangle. Okay. There are 6 different situations here. It's simpler if you split it up into acute and obtuse. I'm not going to try to say that this is simple. This is one of the most complicated pieces of mathematics that we're looking at. But it is not the time to try to memorize these statements. Try going through these constructions again. Try out your homework and let me know how it's going for you, and prepare for communication questions related to this fact.